of light, okay? And that, and again, the official definition, if you want to think of it this way, is a field of science and engineering. So it is both science in the sense of inquiry and fundamental understanding, but also engineering, which is the application of that knowledge, right, to hopefully some societal gain. But nonetheless, the science and engineering encompasses physical phenomena and technologies associated with generation, so the creation of light, the transmission, so the propagation of light, manipulation, which think of it in a couple of different ways. Probably the most obvious way manipulation is to encode information onto the light, or use light as a font to tell a story, so to speak. Detection, because you have to sense it, right? So you've created it, you've encoded information on it. That information is only useful if you see it, read it. And then obviously the greater utility of light. So that's optics in the grand scheme of things. It can be really quite anything from something fairly, what you would think to be low tech, although it isn't low tech, like flip the switch, lights come on, to things that are far more technically sophisticated. We'll talk about a couple of those things as well. But nonetheless, this is kind of where we're going to start. So the value-added application of light, and we will focus on it when the light is being transmitted down a hair-thin optical fiber. So with that definition of light, and you then ask the question, okay, everything from a light bulb to the display, to a projector, to a laser, to what is the economics, right? So Dr. Harrell said I'm the Vice President for Economic Development. So as universities and companies take knowledge that is created and then transfer it into the public domain through companies and other things like that, which is the other part of my day job, what is the economics of light? Again, from all those various applications. And when you pose the question that way, directly and indirectly, in other words, not just light for the sake of light, but light for the sake of something else, like manufacturing. So a laser used to manufacture a car body or something like that. So the economics of all things that are using light in one way, shape, or form, it's about $7.5 trillion per year around the world. Okay, it's a staggering amount of value that is created by light. And again, you come in, you flip the switch on, you log onto your computer, you just assume that the Wi-Fi is going to come on. All of those are optical technologies in one way, shape, or form, and they contribute to this. But optics, some things are very obvious, some things are not quite so obvious where it's being employed. Nonetheless, that's about, on a global annual basis, about half the GDP of the entire United States. Okay, just again, put this in a global perspective. It breaks down, as you can see, into the kind of three generalized categories. There's light as relates to bio and health. That's kind of a big sector. There's light as relates to the things you're probably more familiar with. Telecommunications, optical fiber, things like that. E-commerce, information technologies. That's the biggest of the three sectors. And then transportation, you don't really think, you don't saddle up light and then take it for a ride. But light is used in the manufacturing of pretty much all of your cars, all of your planes. Right? So it's an enabler to those types of transportation technologies. But those are the three kind of principal sectors in which light has its economic value, or you gain economic value from it. So I broke those, or three of those, and change out this way, of where some of these things go, and some examples of them. So in that kind of auto-aero transportation space, pretty much all of the main parts in any modern car are machined today with a laser. Okay, because it's faster, it's cleaner, you can go through thicker bodies, right? So welding, cutting, drilling, you name it, all those things, precision machining. Bio and biotechnologies, probably the more common one you would think of is the LASIK eye surgery, right? But that's a little laser that's poking holes in your eye. Well, not my eyes, but yeah. I don't know. I'm not there yet. I love lasers, but I'm not ready for one to poke me. But also micromachining stents, so it's a little bit different from this machining application. This is on a much, much finer scale. And you can see the precision to which that can be done. Energy, both for exploration, but also now for actually going in and getting it. So we actually have a project funded by this company to investigate new fibers to be used for the actual drilling. So there's a fiber inside this cable that goes down, and a very, very high-powered laser comes through that fiber and actually drills down. Much faster, much more cleaner than normal kind of what you would think of as mechanical drilling. Okay? But that's being done today. I mean, these are real pictures of things that are being implemented. There are various stages of commercial readiness, but nonetheless, it's being done today. And then there's a huge arena within the defense and security space, right? So projection of power at distances where you don't have people in the way. Lasers are very good at that. This is actually a ship-based high-energy laser source that is used today for shooting down missiles and all sorts of other things. Again, but these are all in use today, contributing to that economic value. Let's talk about communications, just because that tends to be, again, the thing that you may be more familiar with. You've heard of optical fiber. You obviously use the internet. And I throw this out through from some friends of mine at Corning, which is one of the major manufacturers of optical fiber globally. And over at on the side to give you a sense, so 250 roughly million kilometers, right? Million kilometers. So it's 250 billion kilometers. Right, a kilometer is about 2/3 of a mile. Right, so take 2/3 of 250, whatever that works out to be, 175, something like that. Billion miles. I think that works out the way it should be, right? Or that would be meters, but 250 million, 200-ish million miles a year of glass fiber manufactured. Staggering amount. I don't think I put it on the next slide. If I remember correctly, that's about 10 feet of fiber for every single person in the world. So you somewhere in the world have 10 feet of fiber. That has your name on it, okay? But what's also interesting is, you're too young, I think, well, except for Rod, to remember this, but there was this .com, I don't know if you're probably in elementary school at the time, there was a economic scale-up associated with all these, apps. They weren't called apps in the late 1990s, but the .com growth that brought industry to the scaling up the production of optical fiber. Those technologies never really materialized, and then there was this huge glut of excess fiber that nobody had any use for. And so you saw in the 90s this huge scale up of fiber production, and then the bubble burst. But then the real applications came along, all the ones I was showing you about, particularly in the IT space. And all of a sudden it starts coming back up now. So as fiber has matured, and as the technologies have matured, and as your expectations for data availability, Netflix, YouTube, those things, as that has permeated and become expectant, the infrastructure behind it, and again, you don't even know the stuff is in the walls and under the ground and all that has just grown. So there was a great deal of excitement about here. But nobody knows that today we're making more than twice as much fiber than we were at the height of that telecom bubble. Okay, but again, that's how technologies mature. Okay, and this is a prelude to this. Where are things going? Right? If you look at $33 trillion technology payoff. If you look at the areas, and this may be a little hard to see, the areas where kind of the grand challenges, the grand technological challenges of our time are coming, right? You can see some of these things: energy storage, advanced materials, 3D printing, cloud technologies, mobile internet, all those things. And where the opportunities are, fiber has a role to play, either in the conventional optical fiber or the new fibers that we'll wind up talking about. But out of a lot of these enabling technologies for the future, there is a very clear, and this isn't just me kind of waxing poetic. I mean, these are the folks that do this stuff for a living, that the livelihood of their company and their shareholders' stake in it is predicated on this, right? So they tend to know what they're talking about. So fiber is a good place to be. Okay. I shouldn't even ask this. What year were you guys born?
94.
Are you kidding me?
92.
Thank you. I feel a little bit better. So you weren't, so seriously, 91 you weren't?
No.
Oh man, I got to take this slide out. All right, so this is what the world looked like in 1991 from the perspective of internet. Sort of kind of what you think of as internet, but not quite so much. So as you would expect, the more developed countries had internet. Developing ones, something kind of like an early phase of it. Some had even just email, and then some had none, okay? So now you're born, some of you, okay? right? But just take a look at this. So again, the more developing areas begin to get this. 94, it's filling in a little bit more. Later 94, it's filling more. 96, right? 97. And if you're kind of wondering, I don't want to make any, socio-political connections here, but there, it's hard to not if you look at who does and doesn't have connectivity. This is not the point. It's interesting, but this is not the point of it. The point is this: over a short amount of time, right? Look at how that has filled in. Okay? Quickly. It is an example, one of the better examples of how a technology has globalized in such a quick way because information is ultimately what's driving this, and the technology was there. Okay, so how do you make it? Right, at the end of the day, you got to make this. So what is this fiber? Right, it shows you all the things it's used for, how much it's made, where it goes. But how is it actually fabricated? Right, so you come out to our lab in Anderson and you actually see this in practice. So optical fibers are a core class. So there's a very centralized. So it's glass. It's hair thin. Seriously, it's about the size of your hair. Very, very long. It has a centralized core, and then surrounding that is a little bit different piece of glass. Okay, so structurally, it's quite simple. All of these processes, all of the fibers are made using a CVD, chemical vapor deposition process, and that's the basic chemistry. So you take something like silicon tetrachloride, you may mix in something like germanium tetrachloride, you add oxygen to it. At high temperatures, that will react. It'll give you silicon dioxide, sand, silica, or germania if you've added some of that in. And then it provides also as a byproduct the residual chlorine. Okay? It's done typically either inside or on the outside of a tube. A couple of ways of doing this. The chemistry is all the same. So you bring in the reactants. There is a high temperature torch. And when I say high temperature, it's upwards of 2000 C. I mean high temperature. And that provides the thermodynamic impetus to drive the reaction to the right. And you go from gases to the silica is a solid, very, very small particle of solid, but nonetheless a solid, which will precipitate, move, and position and deposit itself on the wall, inside or outside, depending on how you do it, of that tube. And so layer by layer by layer by layer, you take this tube, if you do it that process, and you fill it in with glass, 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 glass. And if you change the chemistry coming in, so a little bit more of the silica tetrachloride or a little bit more of the germanium tetrachloride, then you can change that chemistry from the outside in. Okay, and that's how you build up this exterior and then interior. And then you heat it above where the glass softens, certain temperature, it becomes like taffy, then you elongate it. Okay? The process is all the same, more or less. It has worked extremely well, and by that what I mean is this. So the founders in many ways of the field, here are some of them. So David Payne invented a piece of this. He's the advisor, one of our faculty here at Clemson. He was knighted this year. Don Keck and wife, and his colleagues at Corning, who were the originators of some of the processes, the National Metal Technology from President Clinton, John McChesney, who was at Bell Labs at the time, the Draper Prize, which is kind of the engineers' Nobel Prize. And then in 2009, Charles Kao won the Nobel Prize in Physics for the early days of fiber. What could fiber be used for? Okay, so it's not just practically important, but significant, not just technical advances, but societal impact. I said, but, right? There's always a but. So here it is. You know what this thing is. You've seen this once or twice, I suspect. So you have 100-ish and change elements, right, that you dig out of the earth, more or less. You would imagine having such a palette of options that the combinations of various elements, so if you have 100 things, then the combination of those 100 things is just mind-boggling big, right? So the number of glasses, as an example, that you could make from combinations of these 100 things, right, is through the roof. So you should then be surprised to learn that in the grand scheme of all the permutations that the periodic table provides, that at the end of the day, we use very, very few of them to actually make glass, let alone optical fiber. So commercial optical glasses, so glass window there, outside fibers, they are all based on silica, SiO2, again, beach sand because it's available, cheap. And then you begin to add certain things into it depending upon what properties you want to influence, right? So fluorine changes the viscosity of the melt, it changes the optical properties. Phosphorus raises some of the optical properties, such as refractive index, it lowers viscosity. Germanium raises the index, doesn't do a whole lot to anything else. Aluminum and boron change the glass structure a little bit, make it more, again, more fluent, drop the melting temperature and the glass transition temperature. You can add some of these other lanthanide elements in to make the glass create light. Okay. So again, depending upon what you want to do, those of us who study this will go to the periodic table and say, okay, I need a glass that does this. I'm going to pick off of my spice rack this, and this, make a glass. It does what you want it to do. Okay. But again, at the end of the day, you're essentially throwing away all these other things. Okay. And there is a reason for this, and here is some of that reasoning. So go back to the process. So here's that chemistry that you're going to rely upon to make that fiber. Right, so material selection, the periodic table, the selection of the materials that you use to make that glass are actually not any longer determined by the properties you want of the glass. They're determined by the process you use to make it. Does that make sense? Right? Normally, somebody comes along and says, I need a material that behaves like this. And we will say, okay, we know the periodic table. We pick these things, and here we'll make you something. But that's usually how it's supposed to work, right? We make a material, we choose a composition because it has certain performance. However, what has happened over 40 years of making fiber is that we've gotten so locked into the process for making it that the process is now defining the compositions, because certain compositions you can't make using this process. But everybody's so familiar with the process, right? We're going to stick with it. And that has restricted the available elements that we can use. Okay, and so here are three of the examples. Right, it's a chemical vapor process. Right, so you have to create vapors of these elemental phases. Right, and again, this may be a little hard to see. This is vapor pressure versus temperature, and you want to deposit silica and germania, and you want it to not deposit something like iron, because iron absorbs. If you look at a coffee table, it's green because it's got iron in it. Right? If you want to put light through an optical fiber, don't want it to be green. Okay? Now this is beautiful because at any given temperature, right, there's a huge 12 order of magnitude difference between the stuff you don't want and the stuff you do want. Fantastic, right? It self-cleans, it's self-cleaning. So you can have a pretty crappy, pool of liquid. You warm it up, the vapor begins to evolve off. It's 10 to 12 times purer than what was in that liquid. Great, okay? So that's good. However, you have other things that you may want. Aluminum you could want, gallium you may want. So there are these big vapor pressure differences that restrict portions of the periodic table. This is refractive index. It's hard to see. But again, you need to confine the light in the middle of the fiber. That requires you to have a denser, more optically dense core than the cladding that goes around it. Certain things raise the index, certain things lower the index. Right? But you want higher in the middle, so again, periodic table just got a little bit smaller for us. Thirdly, you need to co-process the center and the surroundings, which means that they have to have a similar viscosity at the temperature that you're making it, right? And again, certain things, right? So here's silica, beach sand. Here's like normal lab glass, Pyrex. Okay, huge difference in viscosity for a given temperature, right? So this is or 1 over temperature. This is temperature. You pick your temperature. The viscosity is either here or it's way down here. That you cannot co-process those glasses. So all of a sudden, your periodic table is getting smaller and smaller and smaller, and it gives you ultimately back to where we were. The question, though, then is, well, okay, I understand that, but how do we reopen up that periodic table so that we can today get to where the fibers of tomorrow need to be, for the applications that you want? Okay? There's one other thing, and this is where you have to be a little bit more understanding of the material science, is that certain glasses form better than other glasses. Okay, so let me give you an analogy to this. So oil and water, you know, don't mix, right? So there are equivalent material examples of that, where you take, you take two glasses, almost behaving like oil and water above their melt. They don't mix; they demix. Okay, so you would look at the melt and you would see blobs of the different things, just like you do with oil and water. You, of course, have other systems that mix beautifully well. So those are obviously the ones you want to stick to, because you're going to want a glass that is homogeneous. As the light goes through it, it just sees one thing. It doesn't see this material, then that material, then this material, because it's going to bounce around and scatter, and all your light's going to be lost. Okay? And again, if you look at, so this, you're going to see a few things like this. This is what's called a phase diagram. So it tells you, so this is SiO2, you multiply through by the 2, SiO2, GeO2. In this system, there's complete solubility. So you can mix as much or as little SiO2 with GiO2, no water and oil. Beautifully mixed, okay? And you'll see there's a liquid. So this line defines for you, at any given combination of those two, where the temperature at which that combination melts. So it's a solid down here, it's a liquid up here. Keep that in mind. So for germania, for phosphorus, right? So based on the refractive index, the thermal properties, those other things, and the ability of the glass to play nice with itself, all of a sudden our periodic table shrank down to like 6 things, okay, out of 100. So you've greatly restricted your material availabilities. Okay. When it doesn't work well, it looks like this. And you'll see here, I highlighted it, it says 2 liquids. So if you mix silica and magnesia, which is very, very common in the Earth's crust, or alumina, I mean, these are 2 of the 3 or 4 most common element or minerals, compounds in the world. Look at the chemical makeup of the Earth. These are 2 of the 3 or so. I think iron's probably number 2, silica, iron, and then probably alumina or something like that. 2 of the top 3 or 4 compounds around, right? Can't get better than that. However, you can't mix much alumina into silica without getting what's called a phase separation. Again, oil and water, because the structural elements of the silica and the alumina are different enough that they don't like to mix, not much. Okay? So you can't put much of this in here. And again, your periodic table just got smaller. So what do you do? Right? So I said, you know, what are these demands? So if you look at not just the amount of fiber that's being made, but the amount of information or light that is actually going through that fiber. So think of it this way. You want more Netflix. You want more, whatever the hell you're downloading that you're not supposed to. But you know, you have more information, more light going down that fiber. You can either add more fiber, which is very expensive, can be very expensive because you got to drag it across the ocean or trench it, you know, across campus. Or you say, you know what, fiber is just a very small window. I'm just going to pack more light onto that. And if you're careful the way you can do it, it can be done. However, just like you coming out of the movie theater where it's dark and you come out to the sunlight and all of a sudden it's bright and you can't quite, you know, your materials are not reacting well to that excess of light. Same thing is true with the glass. There comes a point where the glass or plastic or whatever you're using, glass in this case, cannot handle the amount of light you're asking to go down it. Okay? Then all sorts of other things happen. We get into what are called nonlinear effects. One of those is called SBS, stimulated Brillouin scattering. So the vibrations of the atoms and the sound waves created by those vibrations are actually beginning. They don't normally under kind of low light levels. The sound and the light don't talk to each other. They don't know the other one is there. However, at high powers, there's so much light and it's creating so much sound, so to speak, not sound that you can hear, but vibrations in the material, that they do actually begin to interact with one another. Okay? That takes energy away from the light, causes some other detrimental effects, and the fiber in the system itself doesn't behave the way you want it to behave. Okay? So as you have demanded more, you know, movies and video and stuff, and more light is going down the fiber, as we and others are making higher powered lasers for drilling and defense applications, there's more light. There are other things too, higher temperatures, other colors of light, things along those lines. All of these effects that previously nobody cared about because they're so weak are now becoming problematic. Okay? So the question then is, I'll try to speed this up. Well, what do you do? Right? So this is getting to the future part. So fibers have worked very well for 40 years, okay, or 18 years, 20 years of your life. So it worked very well, but only now are we beginning to kind of hit the barrier where the performance is not scalable any longer. So you need a new fiber. Question is, what does that mean? So typically there are two ways to address this. One is you go back to the periodic table and say, okay, the material of today is not working. What is the material of tomorrow? Okay. Problem is, our periodic table is yay big now. So that's not an easy solution to this typically. Okay. But remember, that's predicated on the fact that the manufacturing process is defining the materials, not the performance. Okay? So what people have done instead is to look at all sorts of structure. So when you think of the performance of something, right, it is both the combination of the structure that it's built in and the materials from which it's made. Okay? Structure property. So people have said that, okay, I want to reduce some of these effects. I'm going to go from a very simple core-clad structure to a very, you can't even see, these are so thin, very complicated honeycomb-like structure. This is a fiber. This is the size of a little bit bigger than the size of your hair. But look how complicated that is. Okay? But it's made out of those same standard materials because, again, that's what everybody's comfortable with. We can make these fibers. Our stipulation, or at least what we've been working on here at Clemson, is that that's actually not the solution. Complexity is never, becoming more complicated is never a solution. Okay, or at least it's not a sustainable solution. So what we have tried to do is actually flip the whole thing around and remind people, right, that old is not bad, common is not bad, but remember that the problem we're trying to solve is dictated by the manufacturing, it's not dictated by the materials. So we're trying to return to simplicity and remind people that materials can be an answer to some of these problems. Okay? So what do we do? I showed you how that process is made, or the majority of fiber around the world is made using that chemical vapor deposition process. And now in that case, you deposit all these layers, multiple glasses that are in there. Compositions are such so that they can be co-processed and drawn together into fiber. Usually below their melting point, but above where they soften, like gum, taffy. Okay? What we have done and focused on is really just different a process than that. You take a glass tube, usually pretty thick-walled tube, that draws into fiber again at a certain temperature. And then into the center of that, which becomes your core, that is where you put, again, the material that you want that has the composition that is going to do what you need it to do, that you couldn't make using this other process. But it's selected so that it melts. It doesn't just soften, but it actually melts. It's a liquid at the temperature where that cladding periphery draws then into fiber. So this is fundamentally different in that regard than that previous process. But again, it's scalable. You just keep on drawing. So glass tube, precursor in the middle. Could be a crystal, could be a glass, could be powder. Doesn't matter because it's going to melt. I shouldn't say it doesn't matter, but it matters less because it's going to melt. And there are a lot of advantages. There are some disadvantages, but what I kind of somewhat tongue-in-cheek say is you have to understand the material science of this, which most people don't. And I'm not saying we always do, but in the grand scheme of optical fiber, it's largely led by physicists and, no offense, electrical engineers who don't know a whole lot about materials. Some know more than others, but as a general disciplinary rule, they don't. So let me give you an example of this. And since you're students, I'm going to throw in an educational point, is that when this whole thing started for us, well, actually, you know what? Let me walk you through this first, and then I'll explain it. So YAG is yttrium aluminum garnet, very well established crystal. Right? All the atoms are lined up crystal, not glass. It is a wonderful, it is used a lot as the source for making a laser. It's an excellent laser material, high thermal conductivity, so as it generates heat, it pulls it away. Well established, high purity is available. It's great. It is one of the classic kind of materials when it comes to lasers. We were asked to make a fiber that had as its core, YAG, as a crystal, which, again, we don't have to belabor it, but it's a very difficult thing to do. There was evidence in the literature by a group in Asia that this could be done. We had our suspicions, but we were asked to do it. We tried replicating what was published, didn't work, right? So what we were actually funded to do did not work, okay? So by that sense, it was a failure. But you have fiber, you say, well, you know what, this is still kind of interesting. It wasn't a crystal, it was a glass. Nobody's ever made this before. Let's check it out and see what it does do, right? So the failure in that sense is not the end. It is, well, it didn't work that way, but again, there may be more to this than that. It also led us to go back and prove why the other group had done things wrong or misinterpreted their data. And so there's a paper out there that's just wrong. So the other message in here is the vast majority of what is published, probably not I should say vast majority, but because it's published, whether it's in a journal or on the internet, doesn't mean it's true, okay? But we, again, draw kilometers of the stuff, we doped it, but again, the YAG melts at a temperature below the softening point of the draw temperature of the glass itself. But we wound up having, this is what the fiber looks like today. I mean, it looks like a very standard, simple fiber. Glass clad, glass core. That is a far simpler design than the one I just showed you with all the honeycombs and all that. Far simpler to make, far cheaper to make. But what does it do, right? Again, it's got this kind of strange composition, don't worry about that. But here's the composition. So the cladding is out here on the sides. This is a compositional probe. So the cladding, that periphery, is pure silica, what we expected it to be because it was a silica tube. The center has the yttrium and the, don't worry about the ytterbium, the yttrium and the alumina from the YAG, but obviously it also has silica, which wasn't there in the crystal. So the silica obviously dissolves in from that glass, right? But you wind up having this composition that you would never be able to make using that other process. So you're sitting there like, well, it worked. I got a strange composition. Nobody's ever studied it before. What does it do? Okay. First indication of what does it do that's different is this. So you can't actually see the light coming in because it's infrared. Can't see it. But when the infrared light comes into a standard fiber of this, with that same additive that makes it create light, it creates a tremendous amount of blue. That's actually bad. I mean, it's a great picture, but you don't want the blue. You shine the same amount of light into this other fiber and it generates far, far, far less blue. And that was one of the first qualitative suggestions that, whoa, that isn't supposed to happen. I mean, that's good, but it isn't supposed to happen. So what's going on? So again, if not for the mistake, probably wouldn't have ever thought about doing this. And if not for the publication of some faulty data, probably wouldn't have tried this either. So I'd mentioned this Brouwen, which is this acousto-optic interaction between the sound and the light, right? And if you go into the physics of it and you say, okay, what is it in the material that impacts, that translates the optical power into this acoustic power? It looks like this, right? So N is the optical density, the refractive index, the photoelasticity, so the ability of the material to convert optical energy to acoustic energy, so to speak, how squishy, optically squishy, acoustically squishy. The wavelength, the density, the acoustic velocity, the line width, so don't worry about that. Some of the things you have no control over, 2 pi, lambda c, right? I'd love to have control over the speed of light, but it's out of my domain. These other things are material properties, though, and so you can influence them by that periodic table. So again, if you want to mitigate some of these challenges, right, and these other things are a little bit more complicated, then now you have a material way to do it. So you don't have to make something so complicated. You have to choose materials that have, low these things and high these things. So again, you go back to the periodic table, you're no longer restricted by the process because you've got a new process. And as long as it melts, maybe. Okay? So what does that look like? So a standard telecommunications fiber has these values for those properties I mentioned before that we have some material control over. We measured those in that case, in that YAG-derived case. And with the exception of one, which is the index or refraction, they all change in the direction you need them to change. Okay? And so there's one frown. Everything else is a smile. Okay? So in order to reduce these detrimental effects, again, without even thinking about it, we had no idea what was going on. This turned out to be actually a very, very important step forward because with this essential mistake, which was very cheap and easy to do, honestly, it behaves as good as the most sophisticated one of those crazy structured fibers that is so difficult to make. There are probably 4 or 5 groups in the entire world that know how to do it. Okay, So very, very complicated fiber, very expensive, almost nobody can do it right. There's nothing on the market out there because it's so hard to make. There's no economy that can make it commercially viable, very few. And with one mistake and almost no cost, you have something that performs just as well in a much simpler design. But then you begin to say, well, okay, now that we're beginning to figure this out, the periodic table is open to us again, what would you choose? So we went back to this other case, alumina. Remember, I mentioned before that there's this immiscibility. So alumina is a great additive to silica, except for the fact that nature doesn't let you put much in. Oil and water, okay? You would love to be higher for the reasons of that thing I just showed you. But there is this problem. But remember, we don't care about this because we operate way up here, right? So we've removed ourselves from the region where this has become problematic. There is a problem, though, nonetheless. We typically draw the silica cladding at 1925, 1950 centigrade. Alumina doesn't melt till 2050. Oops, there it is. So it doesn't qualify for what I had said. Melts below the drawing thing, right? But this is where the nice thing about glass is that it's kinetic. So you can influence its properties by time, temperature, and size, right? So if I take a very thin tube of glass, I don't have to heat it very high because there's not much material there. If I have a big, thick piece of glass, I got to dump a lot of energy in to get it to start flowing. So we decided to go with a very thick tube instead of a thinner tube that artificially kind of raises the effective temperature, draw temperature up to above that melting point. And now it works. As the silica dissolves in, the melting point, the liquidus temperature decreases, we can get a lot of alumina in. And because the fiber is so thin after you draw it, it quenches so quickly, you traverse that immiscibility, you traverse that instability region so fast that the chemistry, the material doesn't have time to separate. Okay? Boom, quenches in, and would otherwise never be able to make, right? All over this entire region. So you do that same analysis. I'm going to speed up. Now all of a sudden you're off scale. Again, there's one thing that's, changed but not so bad. Some of these things are just crazy good, right? So now you're about 100 times better than anything that had ever been made before at that point. This is fascinating here too, because again, it's one of those things why is it so good? It isn't just that these numbers fall into these equations. There's got to be more to it than this. And what we hadn't realized, because again, nobody had ever studied this before because you couldn't make these glasses before because you were wed to this manufacturing process, is that when it comes to this acousto-optic kind of squishiness, silica has a positive value. So depending on how you want to think about this, as a light wave moves through, the effect on the sound is opposite than in the case of alumina. But what happens if you take, to your question before, right? If you take a material that has a positive property and you mix it with a material that has a negative property, what happens? Or at what? You probably know where I'm going with this, right? There's a mean value theorem to this, right? That suggests there's some combination where those things balance, right? So if I have a certain amount of this, a fairly high amount of this, it cancels the smaller amount of this and conceivably get to a zero, right? So some of the most fundamental problems that fiber and lasers today face is something we might actually be able to completely, not just reduce, but I mean completely do away with. I can't think of the last time that a physical phenomenon has actually been completely eradicated. But this is an opportunity. So you look at that and you say, okay, well anyway, so we measure the properties as a function of concentration, and indeed it goes down as you would expect. There are other benefits of this that we don't have time to get into, such as things where as you heat it up, it doesn't change, which is quite nice, especially if you're going down in the earth to drill. So there are all sorts of record things that are associated with this. But here's what I was getting to. So this is that Brouin, that acousto-optic interaction as a function of composition. These are the materials that we made. But again, because this has a negative value, positive value, there is a point at which the mixture of those two things goes to zero. Very few phenomena that do that. Okay, but this is one, and it happens to be the thing that's most problematic. But now that you think about it, again, now that you understand this in more detail, you go back to that periodic table because you don't have those restrictions, and you say, okay, well, what other materials have a negative photoelasticity such that when I mix it with silica, this happens, but it happens maybe at a composition that is much more reasonable for us to make. That is not a particularly easy composition to do. Okay? So again, it starts with a mistake. But a mistake is never, it's a means to a different end, right? Is really all a mistake is. So now you say, okay, my endpoint was here, but you know what, I can't get there. Now I'm going to go over here. This opened up an entire other field. Now you go back to the periodic table and say, you know, all of you are almost now available to me, not just these, because we also have another manufacturing method. With that in mind, which of you have a negative photoelasticity? Not just a negative one, but a large and negative one. Because then this is really going to go through the roof. So we found barium oxide, which again has been around, and I think I mentioned this here, like 68. Okay, 68. I think let me see if I did that somewhere else. Oh, sorry. Did I? Well, anyway, I'll do it later. But people have been studying this for a long time. Barium oxide. I mean, it's about as boring as it gets, seriously, from a materials perspective. So pure barium oxide, starting with silica glass cladding. You draw it, some of the silica dissolves into that core. But again, look how simple that is compared to what you saw before. Here's that phase diagram again. Pure baria, silica, pure silica, adding baria in, huge immiscibility, could not make this fiber with even a pinch of the barium oxide in it. It has about 10 times more negative photoelasticity than the alumina. So the composition should go to much, much lower barium oxide concentrations. Again, we draw it. It does exactly what the silica comes in, does all this stuff, right? Beautifully simple. Again, I don't want to bore you with some of these other things. There are temperature and strain independent properties, which again, very unique to this. Again, that composition which goes to 0, which again, we haven't hit yet, right? Students of mine, right? Haven't hit yet. We've gotten pretty close. But again, you're down by almost a factor of 100 compared to what else is out there, right? But again, more reasonable compositions. Okay. And if you kind of overlay all of those things together, right? So the YAG one that we started with actually doesn't do it, doesn't show that because it doesn't have that negative photoelasticity. But it does have a reduced photoelasticity, which gives you a reduced acousto-optic Brillouin interaction. But when you begin to mix in the materials that have the negative photoelasticity, all of a sudden you get the possibility for these zeros. And if you're more thoughtful about it, you can begin to push this towards, again, compositions that are not all that crazy. But it required you to do two things. One is not be married to the traditional manufacturing process, not accept the fact that the periodic table exists of 6 things, right? But then understand kind of what was happening, and then how does that, based on that, where do you then go? Okay, we've done some other materials we didn't talk about here. They do all the things that we want them to do. Here is the other thing. Oh, this is what I wanted to show you, pre-Google, right? 1918, 1927. You actually, the white building over here is called a library, right? That way, right? And they have these things called books, right? And in those books are issues, and in those issues are articles, and the only way to find them is to actually walk over there, go past the coffee shop, go up the stairs, and actually pull them off, blow the dust off the top, open them up, and you find magnificent papers from 100 years ago that did a lot of the things that we're talking about, or the materials side of things. Anyway, here is the other thing that's very important for you to think about is everywhere in the world when you make glass, because silica, SiO2, beach sand, is the thing that dominates the composition, right? What you do is you start with sand and you mix something else into it, right? So it starts with sand, you mix other stuff in, the composition then is some combination of all those things. So if you want a silica-rich glass, you start with silica and you dilute it, right? So it's almost like, you want to make coffee, right? So you start with water and you put the, right, it's hot water and you put the coffee beans, the grinds into it, right? And you essentially you dope the water with the coffee. So usually you start with silica and you add other things, magnesia, alumina, whatever. So you're starting up here and you're adding other things into it. And that's the problem, right? What we've done essentially is to say, you know what, that only worked. That's part of the reason why the periodic table is so small today. We do something different. We start, as I said, in the middle with pure alumina or pure magnesium aluminate, spinel, or barium oxide. We start on the complete other end. And as it melts and it interacts and dissolves in some of that glass, it actually goes this way. It goes towards that other composition. So we're making a glass that has a high silica content by starting with something that has no silica in it whatsoever. Again, that's extremely counterintuitive. But it's the only way to work. And again, you don't think of these things until after you've thought about it and studied it, right? So forces one to rethink how you formulate glass. Conventionally, you batch it, you melt it, you homogenize it, you cast it, you anneal it. In that case, you deposit the vapor, but you're always starting with silica and doping it, right? So we're doing the opposite. And what that gets you to, so this triangle is the same triangle as I just showed you before, but even though we start with something that has no silica in, and we end with something that, in that particular case of the spinel, is 93, I forget what it was, 93% silica. We dissolved 93% silica into this thing. It gets you to a composition that you otherwise still couldn't make because it's that immiscibility. You couldn't do it using the conventional route. But again, it opens up, it obviates all these immiscibilities, many of them at least. Okay? So, that said, time is running out, I think. Straightforward method, because again, this isn't crazy. This isn't all that difficult. I have the pleasure of being able to say that because I don't actually have to be the one in the lab who does it. So I say it's straightforward. And you guys can differ. But you take these standard, common materials that are all, that are easy for, to go out and buy. We've learned a lot along the way about the thermochemistry, whether it needs to be crystalline or amorphous, right? But the phase diagram is very important to that. There's always more to do, more understanding, getting the properties even better. But again, at the end of the day, there's so much today that is talked about, nanotechnology and all these other types of things. Because they're sexy, they're different, they're new, they're unexplored, but quite honestly, a lot of the same things that people have been working on for 100 years are just as interesting and are probably in many ways much more practical and likely to actually have an impact. But you have to figure out where they are. Okay. So, I said before that this mistake behaves optically or acousto-optically the same as this far more complicated structure. Okay, and that's what we're trying to do, return to that type of simplicity. You have to, and as I said before, boring rather than complex. And there is a role for material science to kind of regain that mantle. Okay, Courtney loves this one. Just because you have a sense of what's going on doesn't mean it always works the way you think it's going to work. Okay, so we were asked to make a silica ytterbia. Okay, strange composition, I understand, but So we made a fiber that, again, on average had about 50% ytterbia, which was off scale. Off scale good. But what's interesting is you look at that phase diagram, and again, here's your two liquid immiscibility, right? So you want to stay away from this. So we said, well, you know what? We don't need a hot. 50% is a lot. If we got 20 or 30%, that would still be fantastic. So we stayed way down here, because we knew if we got over into here, it'd be a problem. So this goes under the, like I said, careful what you wish for. So we started with this composition because, again, it has to melt. So it melts, we're above the liquidus, it melts here as we draw it, 40%. But we under-anticipate, well, I under-anticipated how much silica would actually dissolve into that melt. And what we wound up doing is starting here, thinking maybe it would wind up over here somewhere. Started here, wound up, by the time we were done, being over here. 50 weight percent, 86 mole percent, which is what's measured here, is smack in the middle of that immiscibility. So again, if you're doing this, but you're way up here above the melt, it's not probably a big deal because up in the melt, it's homogeneous. And then you quench so quickly, it gets locked in that homogeneous liquid. We were here During the melt phase, it moved over into here, two liquids, two immiscible liquids. That's where the problem is, and the fiber you get looks like that. Looks like your oil and water that has been frozen in. Okay? That doesn't behave very well, as you would imagine. Anyway, there's still a lot to do, but again, you do have to be very mindful of these types of things. And I believe that's it. So thank you for your time. If you have any questions, I'll do my best to address them, and I hope you enjoyed learning something about fiber. Somebody had, okay.
So I guess I was wondering, does the benefit of reducing all those acoustic interference effects outweigh the increase in the refractive index?
Ultimately, no. Well, I shouldn't say that. It depends on the application. As a first response to the community that says, look, here's a new route to making these new types of fibers, here's the performance and how it's improved, it was an important first step. Ultimately, what we would have to do is get that same reduction, not change the index as much. So we would have to look for other things that had just as big a change in, say, that acousto-optic effect, and there are other ones too, other effects too that you might want to reduce, without having such an effect on the index. And if we can balance those things, so you want to be able to balance the index, you want to be able to balance that acousto-optic. Actually, there are two different types of acousto-optic interactions. I only told you about one of them. So both of them, ideally, we were talking about this the other day, if you can make the perfect fiber, right, it would have a pretty specific and fairly small difference in index. It would have none of either of these two interactions. Now again, none. Do you really need none practically? And the answer is no. If you can reduce it by probably a factor of 10, or better yet, a factor of 50 or 100, you don't need 0. You need 100 times reduced, and everybody would be thrilled with that. You would want it to not really change much if it got hot or cold, things like that. But again, those aren't crazy difficult things to do. They just require, I believe that within the periodic table, the combinations are there. We just haven't found them yet. But in the last, I don't know what this has been, 2 years or so, again, making a mistake, figuring out how it behaved, realizing that there was an opportunity there, and then understanding why it behaved as it did, and then with that understanding, going back to the periodic table, which now has opened back up somewhat, knowing what then to look for. Right, that's been the process. Sure. So, but it's always a trade-off. But I think in the end, those are manageable trade-offs. So quiet. Yeah.
In that the diagram of what you created, there's the center point and then whatever surrounding it. Mm-hmm. Is the center point the most important part of the center? Does the outside matter?
Yes, the outside matters for a couple of reasons. One is that, well, I guess two main things. One is that the ability of the light to be carried down the fiber depend both on that central core and the optical properties of that cladding. So like that refractive index we were just talking about. So the optics of that cladding matter. The other piece that really matters is the outside from a strength perspective. Right? You don't want this just breaking in your hands. You got to, clad it. You got to jacket it. You got to pull it through the ceiling. So it's got to be really, really, really strong. So that also somewhat defines the behavior of that cladding.
Is it also feasible some days, maybe not just at one point in the center, but if you had a certain smaller structure? Yeah.
As a matter of fact, a lot of the more specialty fibers today that are being thought about for data centers, we have, again, lots of lasers sending lots of information, have multiple cores in them. Usually some hexagonal stack of 17 different cores. But that's the nice thing about this is you start with that tube, and that tube in our case just has one central hole. But there are tubes that have 17 holes in them. You have them manufactured that way, and then we would just drop our material into each of those 17 and draw it together. But yeah, there are fibers today that people are making that are what are called multi-core for exactly that reason, trying to get even more information down that fiber. Yeah.
Are those, I guess just from my own understanding, are the acoustic interferences like similar to phonon scattering? And
Yes. So it's exactly what it is, or it's a form of it. So you have different types of phonons, right? You have an acoustic phonon, you have optical phonons, and so depending upon the light, which the light is scattering off of which, and what those effects are, you get into kind of these different nonlinearities. What winds up happening in this case, though, is the light goes down. The light is a wave, right? So you set up these where the light is the strongest. It sets up stronger scattering, stronger vibrations, and then those begin to create an optical grating in the material, which then feeds the light. So the optical grating creates the material grating associated with the constructive interference of those vibrations creates an optical grating, which then the light interacts with and starts sending it all the way back. So it creates the acousto-optic interaction in that case creates essentially an optical filter that sends the light you're trying to get through it back at you. That's the problem.
A generic question. You may have addressed this, but what technology or technologies would you say is most limited by current limitations in optical fiber? And let me just elaborate that. I can remember a long time ago there was a big deal made about a lot of phone traffic was now being carried by optical fiber, and it was going to be a revolution. And now, of course, with these, maybe that's not such a big deal anymore. I don't know.
Yeah, let me do the wireless in a second. The biggest, so the biggest technology areas where fiber is used in terms of volume is defense, particularly, in which case it's an immediate need now because we can't make fibers that lays at higher powers because of these effects. So that's an immediate issue. Telecom is also now running into it, although it's not as detrimental because they do a lot more signal processing and things like that. They more electronic back end than they can do on the high energy laser side. So it is a problem, but the optical network folks are it's not an immediate urgent fault right now, although we know it's coming. So that's kind of the two things. One is now needs to be done. The other one, which is the telecoms, it's imminent, but it's not critical just yet. So the Wi-Fi is interesting, right? So what a lot of people, I think, don't realize is that, again, with your cell phone, with your Wi-Fi, there's a transceiver somewhere. But that information, after that, ultimately still goes through a fiber, right? So when you call somebody, you're not just going Wi-Fi, wireless to wireless, wireless, wireless. It's going, your phone to a receiver somewhere, transmitter receiver. And then on the back of that, or somewhere within the building, is actually the fiber backbone that takes all that information everywhere else. So the wireless piece of this, unless you're like satellite phone or something like that, but the normal kind of Wi-Fi is still all fiber connected. It's really the Wi-Fi is really just that first and last little bit where you really enjoy the benefits of being wireless. Anybody wants their pizza, which isn't here yet?
You give everybody an oral quiz on optical fiber.
Yeah, there we go. Get out some paper. No. So where are you from? Let me ask you that then.
Greenville.
Well, that doesn't count. No, I'm just kidding. Where are you from?
Kentucky.
Okay, that's a little bit better. A little further.
Texas.
Ooh, getting. Or is this? You didn't sit in order of how far you were from here, or did you? No.
We start heading back over here.
Oh, do you? Okay.
Rhode Island.
Oh, I think Rhode Island's still further than Texas. Okay, so the trend continues.
Seattle.
Damn. All right. All right. Go ahead. Bring it back.
Michigan.
Okay, all right. It's still pretty
I'm
far,
Orlando,
though.
but I go to school here.
Okay, great.
New Jersey,
Where from?
near Philly.
Oh, it doesn't count. No, I'm just kidding. I grew up in New Jersey. Okay, great. It's a lot nicer here. Well, it depends on where if you live near Philly or a little bit further.
I'm like in the Cherry Hill area.
Okay.
Yeah.
Yeah, that's nice.
Yeah, it's a nice place.
Yeah, okay. Anything else?
Yeah.
Yes.
From Atlanta.
Okay, that's far enough. So, any other questions?
Anyone has questions? Let's thank our speaker.
All right, thank you.